Hello friends. So in today's lecture I'll be teaching the numericals of reciprocating pumps, which is a semester 8 elective 4 subject. So first of all, what is a reciprocating pump? This, my friend, is a reciprocating pump. It has a crank, a connecting rod, a piston rod and a cylinder assembly. This is the delivery valve and this is the suction valve and this is the sump. So from the middle of the cylinder to the bottom of the total head we have suction head, and from the middle to the last we have discharge head. So these are the basic values you need to remember while solving the pump numericals. Let's start with the first numerical, and we have two types of pumps, single acting pump and double acting pump. I'll be teaching you the difference between them in the coming numerical. So first of all, single acting pump. We will be given certain data including speed, actual discharge, the diameter of the cylinder, length of the stroke, that is the length which piston covers or sweeps. Okay, so we will be asked to calculate theoretical discharge, coefficient of discharge, slip and percentage of slip. So what is theoretical discharge? It is the ideal discharge which the pump should give without the losses at full efficiency. So the formula is ALN divided by 60. That is area into stroke into speed divided by 60. We get meter cube per second discharge. So area will be pi by 4 d square, that is the main cylinder diameter, and L is given and also the speed is given. We have to keep in mind that all the dimension will always be in meter, because for solving the pump it is necessary to calculate it in meters, and the power will be in kilowatt always. So we will calculate Q theoretical as ALN divided by 60. We will get the answer. So second is coefficient of discharge, which is Q actual upon Q theoretical. Q actual will be always given 0.001 meter cube per second, and we are given Q theoretical, so we can calculate coefficient of discharge. Slip is Q theoretical minus Q actual, that is the losses that are occurred in the pump are known as slip. So that will be Q theoretical minus Q actual, so we get the slip. And percentage slip is Q theoretical minus Q actual divided by Q theoretical into 100, which will account to 4.489%. Let's see the next numerical. So this is the second numerical of a double acting pump. We have been given speed, that is 40 rpm, with which the crank rotates. Q actual is given as 1 meter cube per minute. So minute should be converted to second, that is divided by 60. We get 0.01666 meter cube per second. The length is given, diameter of the cylinders is given. We can find out the area. We have been given suction head and discharge head, that is from this middle H atmospheric to the bottom of the sump we get HS, that is suction head. From H manometric to the highest level of discharge pipe we get discharge diameter. Now this is a double acting pump, as I said in the last numerical, that is when it will move inwards, that is the crank will rotate, it will deliver water from this pump, and when it will go outward, that is the crank will complete one revolution, it will flow liquid from this pipe. So this is a double acting pump in which we get continuous discharge in both the strokes, and we have to find out the same power and slip. First we will be calculating Q theoretical. As there are two pipes, we will be having 2 ALN divided by 60. Rest remains the same, and Q theoretical will be in meter cube per second. Now next will be slip. The slip formula is Q theoretical minus Q actual. You can easily calculate the slip and the percentage slip as well. Now comes the power. Power is 2 rho G ALN head upon 60 into 1000 to convert it into kilowatt. 2 is because we have double acting pump, 1 is because when we have single acting pump. So 2 into 1000 into 9.81 into area into stroke into speed into addition or sum of both the head upon 60,000, we will be getting the answer of power as 4.109 kilowatt. Let's see the next numerical. So in this numerical, the given data is provided. We have been given the Q actual in liter per second. So liter should be converted to meter cube, that is divided by 1000, and we get meter cube per second. We have been provided length and diameter of the delivery pipe. So this will be the length and diameter of the delivery pipe, D and L of the cylinder. We are also provided with suction head, I beg your pardon, it's the total head which is given as 25 meter from the ground to the topmost level of the pump's mechanism. So we have to find out Q theoretical, which can be found out easily, ALN upon 60. Theoretical power should be calculated, that is rho G ALN H upon 60 into 1000. So in the power equation, ALN upon 60 constitutes Q, and we have to use theoretical discharge to find theoretical power, actual discharge to find actual power, and we can also find out percentage of slip. So 3 parameters are covered, and the last parameter is accelerating head at the beginning of the stroke. So what is this parameter? What happens is when the crank rotates, it does not move with uniform velocity. For the first half journey, it moves with acceleration, and for the rest half it moves with retardation due to the force of gravity. Therefore, when it sucks water for the first half, it sucks it with a higher velocity or higher pressure or higher head, what you call, and for the rest of the suction stroke, the pressure is down or the head decreases. So we have to find out acceleration head. Now the crank rotates from 0 degree, that is the outwardmost center, to the inwardmost center, that is 0 degree, 90 degree and 180 degree. These are the 3 positions for the crank, and the cycle completes. In this way the pump rotates, the crank rotates, and the pump reciprocates, and water is lifted. The formula for finding out the acceleration head, that is HAD, because we have been asked to find out at the delivery, and so we are provided the delivery dimensions, will be L by G A by A into omega square R cos theta. So we have been given all the dimension. We have the delivery length, we have the area of the delivery pipe, we have the area of the cylinder, we have gravitational force, also we have omega, which can be found out using N, that is 2 pi N divided by 60. Also we have R, that is L by 2 cos theta. Now the question comes, what to use about the theta? So friends, when the suction stroke start, the piston is at the innermost center, that is 0 degree. So we will get maximum head at the beginning of the stroke rather than the end of the stroke. So we use theta is equal to 0 degree to find out the maximum accelerating head. So you see the values of 0. When we put cos 0, we get 1, cos 90 is equal to 0, and cos 180 is equal to -1. This shows that the accelerating head is maximum at the beginning of the suction or delivery stroke. So we have found out the area of the cylinder, we have found out area of the delivery pipe, and we have found out R, which can be used in this formula. So friends, we have to find out at the delivery stroke, we put L by G, that is length of delivery pipe, upon gravitation, area of cylinder to area of delivery pipe, into omega square R cos theta. So that should be giving as 20.75 meter. And also we have to find out the maximum at middle. As I told you, at middle theta is equal to 0, 90 degrees, so cos theta is equal to 0. So we will be getting no accelerating head at the middle of this suction stroke or the delivery stroke. Hence we found out the accelerating head at the delivery stroke. I hope you understood the concept of HAD and HD. HD is the fixed head which we have to lift by the pump, and HAD, that is the accelerating head, is the varying head we get per revolution of crank. So these are the two major head, HAD and HAD, which we will be finding out in the coming numericals. HM will be the manometric head, which is always provided. Okay friends, this is the next numerical we'll be seeing. We have been provided length of the suction pipe, diameter of the suction pipe, both one is in centimeter, one is in meter, converted to meter. So we have been given the cylinder diameter, length of the cylinder, and we have been given suction head, that is 3 meter above the sump. In the numerical or in the question, it may be asked that the suction head is 3 meter above the water level. So we have to understand that it is the suction stroke, and H manometric or H atmosphere is 10.3 meter and N is 35 rpm. We can find out omega, that is 2 pi N upon 60 radian per second. First we have to find out acceleration head at suction. So in this numerical it is suction, in the last numerical it was discharge. So we have the formula, we have L, we have A g omega square r cos theta. So r is L by 2, omega is 2 pi n by 60, a is pi by 4 capital D square, small a is pi by 4 small d square, L of the suction pipe, g. So we find out everything and we put in the formula. Now we get HA as 2.695. This is also the maximum because the maximum is at the beginning. Next we find out the pressure head. So what is pressure head? Pressure head is in terms of meter of water. So we can find out pressure head for suction, H manometric minus HS minus HAS. So remember this formula to find out the pressure head at the beginning of the stroke. This is the formula for pressure head at beginning, H manometric minus H suction minus accelerating. We get 4.605. Meter of water will be the unit and not meter. You will lose marks. Same at the end of the stroke, it will be HM minus bracket HS plus HS minus HAS. So we will be getting 9.995 meter of water. This should be the pressure head at the beginning and end of suction stroke for a reciprocating pump respectively. In the same numerical, if the delivery pipe dimensions are given, so we again find out HAD, that is accelerating head at the delivery, and to find out the pressure head at the beginning and ending of the delivery stroke, we took HM plus HD plus HAD. Now we know why, because delivery is above the atmosphere and suction is below the atmosphere. So this is atmosphere, here lies HD and here lies HS. So HS will always be subtracted from the atmospheric line and HD will always be added to the atmosphere line because we start counting pressure from datum. Therefore this is the datum and we start counting pressure, and hence suction and the delivery pressures can be found out. So pressure head at the beginning of the stroke will be HM plus HD, that is H manometric plus HD plus HAD. So this will be the maximum pressure during the beginning of delivery stroke, and we can find out the pressure at the end of delivery stroke will be H manometric minus HD plus HAD will be the varying stroke. So we can find out end and starting of the delivery stroke. So this is an important numerical which we will solving. We have to find N. In the last numericals we were given N and we were finding the heads. In this numerical we have been given all the heads and we have to find the speed. So this, my friends, is an indicator diagram which is a graph various pressures in a cylinder and the stroke of the cylinder. So this will be pressure and this will be stroke. So during the suction stroke, as the length or the stroke goes on, the pressure increases and the final pressure increases, and during the delivery stroke the pressure reduces and then it again reduces to 0.1. So this is indicator diagram and this shows suction and discharge. This is the sump level. From the sump level to the mid level we have HS, and we also have HAA, that is accelerating head, that is difference between H manometric and H suction is HAS, and this region is called separation region. If the pressure in the pump falls below separation region, the gases dissolved in water will start separating and cavitation will happen, that is only air will be thrown out of the pump and not water. So our pump is designed always above the separation level, and we have been provided separation level in this numerical as 2.5. So clearly understand the indicator diagram as it is very necessary. So we have to find out N or omega, and we can only find this in the formula, that is accelerating head formula, L by G, A by A, omega square. We have to find omega. For that we need accelerating head. Now how to find the accelerating head? In the last numerical we found out the pressure head during the start of suction and end of suction stroke. So similarly H separation is HM, that is total manometric, minus HS minus HAS. We will get H separation. So we have been provided H separation, HS and H atmosphere. We can get accelerating head. From the accelerating head we can put all the values in the formula. Take theta is equal to 0 because we have to find the maximum. So putting all the formulas and values properly in their respective places. Okay, so this is the same numerical which was asked previously, but the separation pressure is given instead of separation head. We have been given 7.848 Newton per centimeter square. First we convert it to meter square, that is 7.848 into 10 raised to 4 meter square, and now we have to convert the pressure into head, that is 7.848 into 10 raised to 4 divided by 1000 into 9.81. We will get it in meter, but it is below atmosphere. So now this separation head is greater than the addition of HS and HAS. So it cannot be greater than HS and HAS, therefore we separate or subtract it from manometric head. 10.3 minus 8. So finally we get 10.3 minus 8, that is 2.3 meter as separation head, and then we can normally solve the numerical, that is finding out HAS. From HAS we find out omega, and from omega we find out R. So this was a kind of numerical where H separation is used to find out omega. Okay friends, this is a new type of numerical in which we have been asked to calculate work done for the first time in a pump. So this is a double acting pump, as you can see from the figure. We have been given all the dimensions, HS, HD, that is discharge head, suction head and discharges respectively. We have been given D is the diameter of cylinder, and we have been given diameter of piston rod, that is dP. So we have been asked that if inward stroke happens and when an outward stroke happens, will the quantity of water discharged from the two pipes will be same? Think about it before listening ahead. I think you must have answered yes, but it's wrong, because from closer observation we can see when this piston moves backward, we get all of the volume to be swept, but when it moves outward, the piston rod occupies some area and therefore water is blocked in the specific area. Hence we get a little lesser discharge as compared to the piston side. So we have been told to find out work done during the suction stroke and the discharge stroke, that is inward and the outward. So it is coupled with a crank, and when the crank moves outward we get discharge from this pipe, and when it moves inward we get discharge from this pipe. So for this formula we have to find out Q1 and Q2. Let's consider Q1 will be without the rod and Q2 will be with the rod. So Q1 is A into L, that is area into length, which becomes volume, and Q2 is A means the cylinder area, small a means the rod area, into L, which will give us this area. So this will be 2 Q1 Q2. Now the work done formula is rho G Q H. Okay, the density of water and the head as well as the discharge we get. So during left to right, when it goes left to right, the crank will rotate from 0 to 180 and the pump will retract. Therefore rho will be 1000, G will be 9.81. Now let's name the two pipes Q2 Q2 and Q1 Q1 respectively. For the inward stroke, we will get a discharge from this pipe which will be sucked from this pipe. I beg your pardon, there is a little change in the diagram. I was mistaken. When the inward stroke takes place, we will get discharge from this pipe, and when the outward stroke takes place, we will get discharge from this pipe. So water flows in, it is compressed and expanded and then discharged. So work done during the inward stroke will be rho G Q2 HS, that is suction and Q2 from this pipe, plus rho G Q1 HD. When it goes inside, water will be sucked and water will be discharged. Therefore we take HD and Q1, Q2 and HS during the inward stroke. During the outward stroke we take opposite. Now take 1000 and 9.81 common and we get bracket. Now these values will be in joule, and as I told you, it will always be in kilojoules or kilowatt. Therefore we divide the final answer by 1000 to get it in kilojoule. So we get the work done as 4.192 kilojoule when we have all the values which are required. Now we have to find out the work done of the piston from right to the left, that is outward. So during the outward stroke, water will be discharged from the side Q2 and it will be sucked from the side Q1. Therefore rho G Q1 into HS because it will be sucked from HS, and rho G Q2 HD because it will be discharged from Q2 side. And we find out the work done again, and hence we get it different because of the simple area difference of the piston rod. So this, my friend, is how to find out work done of a double acting reciprocating pump. This is the last numerical of the reciprocating pump. We have been given air vessel attached to the suction side of the pipe. Now what is an air vessel? You may be knowing from the theoretical studies. We have to find out the flow is taking from the air vessel or into the air vessel. Now we have to find out, we have been given angles as 30 degree, 90 degree and 180 degree for the crank angle respectively, and the formula for the flow is A omega R 2 upon pi minus sine theta. We have been given the speed of the pump, the diameter of the suction pipe, main cylinder diameter and the stroke. We find out capital A pi by 4 capital D square, omega R theta is given, and we substitute all the values in the equation and we get a generalized form of 0.04996 up bracket 2 upon pi minus sine theta. Let's keep the theta unknown for the time being so that later we can substitute all the values and get the answers easily rather than complicating the equations. Now for 30 degree, put theta is equal to 30 and we get answer as minus 0.00682 meter cube per second. Now this is a negative answer. Negative flow shows that the discharge is greater, the suction is greater than the discharge. Therefore some part of suction is getting stored into the air vessel. Therefore we get a negative answer. For 90 degree we get 0.0181 meter cube per second. Positive shows that the flow is being taken from the air vessel, that is water now flows from the air vessel to the delivery pipe. And for 180 degree we get again positive answer. We have been also told to find out the angles at which there will be no flow from the air vessel or to the air vessel. Now this is the reason we created a generalized equation. We can equate it to 0 and find out the angles. So it will be 2 upon pi is equal to sine theta because 0.4996 will go to the right hand side and get cancelled. So we can take sine inverse of 2 upon pi and get 39.32 as the first angle, and subtracting it from 180 we get 140.28. So here are the two angles at which there will be no flow to and fro from the air vessel. We took 180 as maximum because we have been given 3 angles to find out from, and we generally consider 3 angles for the crank rotation of a pump. So these, my friends, are the numericals for pump and blower examination. All the best, and drop a comment if you have any problem. Do subscribe and share to your friends, and keep studying. Thank you.